Everything you have ever seen, every star, every planet, every galaxy, and every human being, makes up less than 5% of the universe. The remaining 95% is something we cannot see, cannot touch, and still do not fully understand. Hidden all around us is an invisible substance that silently controls the motion of galaxies and shapes the structure of the cosmos. Scientists call it dark matter. But what is it? Where did it come from? And could it be surrounding us right now? Today, we journey into one of the greatest mysteries in modern science. Have you ever looked up at the night sky and wondered if what you were seeing was everything that exists? Every shining star, every glowing nebula, every distant galaxy stretching across the endless darkness appears to make up the entire universe. For thousands of years, humanity believed that everything in existence could eventually be seen, touched, or measured. As our telescopes became more powerful, we discovered billions of galaxies containing trillions of stars, each revealing a universe far larger than anyone had imagined. It seemed as though every new discovery brought us closer to understanding reality itself. But then scientists uncovered something extraordinary, something that completely changed our view of the cosmos. They realized that everything we can see, every planet, every moon, every asteroid, every cloud of gas, every black hole, every star, and every galaxy combined accounts for only a tiny fraction of the universe. Nearly everything else is invisible. It emits no light, reflects no light, and cannot be seen by even the most advanced telescopes ever built. Yet this mysterious substance surrounds galaxies, shapes the largest structures in the cosmos, and quietly controls the movement of everything we observe. Scientists call it dark matter, and although it has never been directly seen, its invisible presence is written across the universe itself. It is one of the greatest mysteries in modern science, a puzzle that has challenged astronomers and physicists for decades. Understanding dark matter may one day unlock the deepest secrets of space, time, gravity, and perhaps even reality itself. Imagine standing on a beach during the middle of the night. The ocean is completely invisible, hidden beneath darkness, yet you can hear the waves crashing against the shore. You cannot see the water, but you know it is there because of the effects it creates. Dark matter is remarkably similar. Scientists cannot observe it directly, but they can clearly see its influence on everything around it. Galaxies rotate much faster than they should. Clusters of galaxies remain bound together despite not containing enough visible matter. Even light itself bends in unexpected ways as it travels through space, revealing the presence of an enormous amount of invisible mass. Everywhere astronomers look, they find evidence pointing toward something hidden, something that outweighs all ordinary matter by an astonishing margin. To understand why dark matter became necessary, we first need to understand gravity. Gravity is the force that shapes the universe on its largest scales. It keeps the moon orbiting Earth, holds planets around the sun, and binds entire galaxies together. According to Isaac Newton and later Albert Einstein, the strength of gravity depends on the amount of mass present. More mass creates stronger gravity. This relationship has successfully explained the motions of planets, stars, and countless other celestial objects for centuries. But when astronomers began carefully measuring how galaxies rotate, something unexpected appeared. If gravity depended only on the stars and gas that astronomers could see, the outer edges of galaxies should move much more slowly than their centers. This is exactly what happens within our own solar system. Mercury races around the sun because it is close to its immense gravity, while distant planets like Neptune move much more slowly. Scientists expected galaxies to behave the same way. Instead, they discovered something astonishing. Stars located near the outer edges of galaxies orbit at nearly the same speed as stars much closer to the center. According to every calculation based solely on visible matter, those outer stars should have escaped into intergalactic space long ago. Yet they remain securely bound to their galaxies. This mystery suggested that galaxies contain far more mass than anyone could actually see. An invisible halo appeared to surround every galaxy, providing enough gravity to keep these rapidly moving stars in orbit. The idea sounded unbelievable at first. After all, proposing the existence of an invisible substance throughout the universe was an extraordinary claim. Naturally, scientists searched for other explanations. Perhaps Einstein's theory of gravity was incomplete. Perhaps measurements were incorrect. Perhaps telescopes had overlooked enormous clouds of ordinary matter. But as observations improved over the following decades, every new piece of evidence pointed toward the same conclusion. Something invisible was exerting gravitational influence throughout the cosmos. One of the earliest scientists to notice this strange behavior was Swiss astronomer Fritz Zwicky in the 1930s. While studying a massive collection of galaxies known as the Coma cluster, he measured how quickly individual galaxies moved through the cluster. According to the visible matter present, the galaxies were moving so rapidly that the entire cluster should have flown apart billions of years ago. Instead, it remained tightly bound by gravity. Zwicky calculated that the cluster must contain far more mass than telescopes could detect. He called this missing mass Dunkelmaterei, or dark matter. At the time, very few scientists accepted his conclusion. The idea seemed too strange, too speculative, and too difficult to verify. For decades, it remained little more than an interesting possibility. Everything changed in the 1970s when astronomer Vera Rubin began studying the rotation of spiral galaxies with extraordinary precision. Night after night, she carefully measured the speeds of stars orbiting far from galactic centers. What she discovered transformed astronomy forever. Every galaxy she examined displayed the same unexpected pattern. Instead of slowing down with distance, stars continued moving at nearly constant speeds. The only explanation consistent with gravity was the existence of enormous halos of invisible matter surrounding every galaxy. Rubin's observations provided some of the strongest evidence ever collected that dark matter is real. Today, her work is considered one of the most important discoveries in modern astrophysics, forever changing humanity's understanding of the universe. The more scientists observed the universe, the more impossible it became to ignore the invisible force surrounding it. Every new telescope, every new observation, and every new calculation pointed toward the same conclusion. Dark matter was not an isolated phenomenon found in only a few galaxies. It appeared to exist everywhere. Spiral galaxies, elliptical galaxies, dwarf galaxies, and enormous galaxy clusters all behaved as though they were embedded inside gigantic clouds of unseen mass. No matter where astronomers looked, gravity was stronger than the visible universe alone could explain. The mystery was growing larger with every passing year. One of the most convincing pieces of evidence came from a remarkable phenomenon predicted by Albert Einstein more than a century ago. According to his theory of general relativity, gravity does not simply pull on objects. Instead, it bends the very fabric of space and time. Light, although incredibly fast, must also follow these curves. When light from a distant galaxy passes near a massive object, its path bends, causing the distant galaxy to appear distorted or even multiplied. This effect is known as gravitational lensing. In many cases, astronomers observed enormous arcs and rings of light surrounding clusters of galaxies. By carefully measuring how much the light had been bent, they could calculate the total amount of mass producing the effect. Once again, the answer was astonishing. The visible galaxies accounted for only a small fraction of the required mass. The rest had to be invisible. It was as though gigantic mountains of unseen matter were hiding between the galaxies, silently shaping the path of light across billions of light years. As technology improved, astronomers created detailed maps of the invisible universe using gravitational lensing. These maps revealed something extraordinary. Dark matter was not randomly scattered throughout space. Instead, It formed enormous halos surrounding galaxies and gigantic filaments connecting galaxy clusters across unimaginable distances. These invisible structures acted like a vast cosmic skeleton upon which the visible universe had formed. Stars and galaxies appeared to gather wherever dark matter was most concentrated, suggesting that it had guided the formation of nearly everything we see today. To understand just how important this invisible substance is, imagine constructing a city. Before the buildings, roads, and parks can be built, there must first be a framework, a foundation capable of supporting everything that comes later. Dark matter appears to have served exactly this purpose for the universe. Shortly after the Big Bang, ordinary matter was still incredibly hot and energetic. It could not easily collapse into stars and galaxies because radiation pushed it outward. Dark matter, however, behaved differently. It did not interact with light in the same way. Without being slowed or scattered by radiation, it began gathering under its own gravity, forming vast invisible clouds. Over hundreds of millions of years, ordinary matter gradually fell into these invisible gravitational wells, eventually creating the galaxies, stars, and planets we observe today. In this sense, dark matter may have been the unseen architect responsible for building the cosmic structures that made life possible. When astronomers simulate the evolution of the universe using powerful supercomputers, they find something remarkable. If dark matter is removed from the equations, galaxies fail to form as they exist today. The simulated universe becomes sparse, chaotic, and completely unlike reality. But when dark matter is included, the simulations begin producing galaxies, clusters, and enormous cosmic webs that closely resemble the universe observed through modern telescopes. It is one of the strongest indications that scientists are moving in the right direction. Even though dark matter remains invisible, every successful simulation reinforces the idea that it plays a fundamental role in shaping the cosmos. One of the most dramatic demonstrations of dark matter occurred in a collision between two massive galaxy clusters known as the Bullet Cluster. When these clusters crashed together millions of years ago, the ordinary matter behaved exactly as expected. Clouds of hot gas collided violently, slowing down and producing enormous amounts of X-ray radiation. However, the gravitational mass measured through gravitational lensing continued moving almost unaffected, passing straight through the collision. The invisible mass had separated from the visible gas. This observation stunned astronomers because it suggested that whatever dark matter is, it interacts very weakly with ordinary matter and even with itself. Unlike gas, dust, or plasma, it seemed capable of passing through enormous cosmic collisions almost as though nothing had happened. The Bullet Cluster remains one of the strongest pieces of evidence supporting the existence of dark matter. Despite decades of research, one simple question continues to puzzle scientists. If dark matter is everywhere, why can't we see it? The answer lies in the way it interacts with the universe. Ordinary matter constantly interacts with electromagnetic radiation. Atoms absorb light, reflect light, and emit light. Every object we have ever seen is visible because of these interactions. Dark matter appears to behave completely differently. It neither emits nor reflects light. It does not glow when heated. It does not cast shadows. It remains completely transparent to every wavelength of electromagnetic radiation currently known. If an enormous cloud of dark matter surrounded our solar system, we would never see it directly. The only clue to its existence would be the gravitational effects it produces. Scientists estimate that roughly 27% of the universe consists of dark matter, while ordinary matter makes up less than 5%. Even more surprising, the remaining 68% appears to consist of another mysterious component known as dark energy, which is causing the expansion of the universe to accelerate. Together, dark matter and dark energy account for approximately 95% of the cosmos. Everything familiar, every mountain, ocean, tree, animal, human being, planet, and star, represents only a tiny fraction of reality. In many ways, humanity has spent thousands of years studying only the visible surface of a universe whose true nature remains largely hidden. This realization has transformed modern astronomy into one of the greatest detective stories ever undertaken. Every observation becomes another clue. Every galaxy acts as a witness. Every beam of bent light tells part of the story. Scientists are piecing together evidence from across billions of light years, slowly revealing the invisible architecture that governs the universe. Yet, despite all this progress, one profound mystery remains unanswered. We know what dark matter does, but we still do not know what dark matter actually is. It has never been captured inside a laboratory. No telescope has ever photographed one of its particles. Its true identity remains hidden behind the effects it leaves on the cosmos, making it one of the most elusive and fascinating mysteries in all of science. For decades, scientists have searched for a simple answer to one of the biggest questions in modern physics. If dark matter is responsible for holding galaxies together and shaping the universe, then what is it actually made of? Unlike ordinary matter, which consists of familiar particles such as protons, neutrons, and electrons, dark matter appears to follow completely different rules. It possesses mass because it creates gravity, yet it remains invisible because it does not interact with light. This unusual combination has forced scientists to explore entirely new possibilities, leading to some of the most ambitious experiments ever conducted. One of the earliest ideas suggested that perhaps dark matter was simply ordinary matter hidden from view. Maybe vast numbers of cold planets, burned-out stars, black dwarfs, or isolated black holes were scattered throughout galaxies, escaping detection because they emitted little or no light. These hypothetical objects became known as massive compact halo objects, or MACHOs. For years, astronomers searched the skies hopping to find enough of these invisible bodies to explain the missing mass. Using a technique called gravitational microlensing, they watched millions of distant stars, looking for tiny changes in brightness caused by unseen objects passing in front of them. Although some hidden objects were discovered, there simply were not enough. The numbers fell dramatically short of what would be required. Ordinary matter, no matter how cleverly hidden, could not account for the overwhelming amount of missing mass in the universe. As that possibility faded, attention shifted toward entirely new particles that had never been observed before. Among the leading candidates were weakly interacting massive particles, commonly known as WIMPs. These hypothetical particles would possess mass and therefore create gravity, but they would interact so weakly with ordinary matter that trillions of them could pass through your body every second without leaving the slightest trace. If WIMPs exist, they may fill every corner of the universe, flowing silently through planets, stars, and even living creatures without being noticed. This idea fascinated physicists because it naturally explained why dark matter had remained invisible for so long. To search for these elusive particles, scientists built some of the most sensitive detectors ever created. Deep beneath mountains and underground laboratories, enormous tanks filled with ultra-pure liquid xenon, argon, and other materials wait in complete darkness. These facilities are shielded from cosmic rays and natural radiation by hundreds of meters of solid rock. The goal is simple but incredibly challenging. If a dark matter particle collides with an atom inside one of these detectors, it might produce an incredibly tiny flash of light or a faint electrical signal. Even a single confirmed event could completely transform our understanding of the universe. Yet year after year, these experiments continue operating in silence. They have become increasingly sensitive, capable of detecting interactions smaller than ever imagined, but dark matter remains frustratingly elusive. Another intriguing possibility is that dark matter consists of particles known as axions. Unlike WIMPs, axions would be extraordinarily light, almost unimaginably small in mass. Despite their tiny size, enormous numbers of axions could collectively produce the gravitational effects observed throughout the universe. Scientists have developed specialized instruments designed to detect the subtle signals these particles might create when exposed to extremely powerful magnetic fields. Around the world, laboratories continue listening for whispers from these invisible particles, hoping to reveal one of nature's deepest secrets. Meanwhile, some physicists have proposed an even more radical possibility. What if dark matter does not exist at all? Perhaps the problem lies not with missing matter, but with our understanding of gravity itself. According to this idea, gravity may behave differently across enormous cosmic distances than Einstein's theory predicts. This concept gave rise to alternative theories such as modified Newtonian dynamics, often called MOND. Instead of adding invisible matter to the universe, these theories attempt to adjust the laws governing gravity. In certain situations, they successfully explain the rotation of individual galaxies. However, when applied to galaxy clusters, gravitational lensing, and the large-scale structure of the universe, they struggle to match observations as consistently as dark matter does. While research continues, the majority of evidence still favors the existence of an invisible form of matter rather than a complete revision of gravity. One of the most remarkable aspects of this mystery is that dark matter may be passing through Earth at this very moment. As our planet orbits the Sun and the solar system travels around the Milky Way, it moves through an enormous halo of invisible matter surrounding our galaxy. Every second, countless dark matter particles may flow effortlessly through our atmosphere, our oceans, our cities, and even our own bodies. Yet because they interact so weakly with ordinary matter, we remain completely unaware of their presence. It is an astonishing thought that an invisible ocean of unknown particles could be surrounding us at all times without producing any sensation whatsoever. The search for dark matter has expanded beyond underground laboratories. Particle accelerators such as the Large Hadron Collider near Geneva attempt to recreate conditions similar to those that existed just moments after the Big Bang. By smashing particles together at nearly the speed of light, scientists hope to produce new particles that may resemble dark matter. If such particles are created, they would likely escape the detectors without being seen directly. However, physicists could infer their existence by measuring missing energy and momentum after each collision. Although the Large Hadron Collider has made many important discoveries, including the Higgs boson, definitive evidence for dark matter has yet to emerge. The mystery becomes even more fascinating when scientists look back to the beginning of the universe. Shortly after the Big Bang, temperatures were so incredibly high that particles constantly formed and disappeared in a sea of unimaginable energy. As the universe expanded and cooled, many particles vanished forever. Some physicists believe dark matter particles may have survived this early cosmic era, remaining stable for more than 13 billion years. If this idea is correct, every dark matter particle drifting through the universe today could be a direct survivor from the first moments after the birth of time itself. Studying dark matter would therefore be like holding a fossil from the dawn of creation, offering a glimpse into conditions that existed before stars, galaxies, or even atoms had fully formed. Every new experiment brings humanity one step closer to solving this extraordinary puzzle. Whether the answer lies hidden inside underground detectors, particle accelerators, future space telescopes, or entirely new theories of physics, one fact remains certain. Dark matter has already changed the way we understand the universe. It reminds us that reality is often far stranger than imagination, and that the greatest discoveries are sometimes not about what we can see, but about learning to recognize the invisible forces that have been shaping the cosmos all along. Even though dark matter has never been directly observed, its influence reaches across the largest structures in the known universe. When astronomers map the positions of millions of galaxies, they discover that galaxies are not scattered randomly through space. Instead, they are arranged in an enormous network known as the cosmic web. This web stretches across billions of light years, forming immense filaments connected like the strands of a giant spider's web. At the intersections of these filaments lie massive clusters of galaxies containing thousands of individual galaxies bound together by gravity. Between the filaments are vast cosmic voids, regions so empty that they contain almost no galaxies at all. Scientists believe that dark matter forms the invisible framework of this gigantic structure. Long before the first stars ignited, invisible clouds of dark matter were already shaping the universe, pulling ordinary matter toward them through gravity. Without this hidden framework, galaxies might never have formed, and the universe would look completely different from the one we know today. Imagine looking at a city from high above at night. You see glowing roads connecting neighborhoods, bridges linking distant districts, and bright intersections where everything comes together. Now imagine turning off every light in that city. The roads would still exist even though they could no longer be seen. In many ways, dark matter acts like those invisible roads of the universe. Galaxies are simply the glowing lights that reveal where the hidden structure already exists. Astronomers cannot see the roads themselves, but they can trace their paths by observing the galaxies that follow them. One of the most fascinating aspects of dark matter is that it appears to be incredibly calm. Unlike ordinary matter, which constantly collides, heats up, emits radiation, and undergoes violent chemical reactions, dark matter seems almost completely indifferent to everything around it. It passes through stars without burning, through planets without slowing down, and through enormous clouds of gas without leaving visible traces. Its only significant interaction appears to be gravity. Because of this quiet behavior, dark matter has remained hidden for billions of years, while silently controlling the architecture of the cosmos. As telescopes became increasingly powerful, astronomers began looking farther into space than ever before. Since light takes time to travel, observing distant galaxies is equivalent to looking back into the past. Some of the galaxies visible today formed only a few 100 million years after the Big Bang. Surprisingly, many of these early galaxies already appear larger and more organized than scientists originally expected. Their rapid formation suggests that invisible gravitational structures were already present, helping matter gather together much faster than ordinary gravity alone could achieve. Once again, dark matter provides the simplest explanation. It seems to have acted as the invisible foundation upon which the first galaxies were built. The James Webb Space Telescope has opened an entirely new chapter in this investigation. By peering deeper into the universe than any telescope before it, Webb allows astronomers to study some of the earliest galaxies ever observed. Every new image provides additional clues about how galaxies formed, evolved, and interacted with the invisible matter surrounding them. While Webb cannot see dark matter directly, its observations help scientists test competing theories by comparing the real universe with computer simulations. Each new discovery either strengthens or challenges our understanding, bringing us one step closer to solving the mystery. Meanwhile, powerful supercomputers continue creating virtual universes inside laboratories. These simulations begin shortly after the Big Bang and allow scientists to watch billions of years of cosmic evolution unfold in just a few days. The computers calculate the motion of countless particles under the influence of gravity, revealing how galaxies gradually emerge from tiny fluctuations in the early universe. The results are astonishing. When dark matter is included, the simulations produce beautiful cosmic webs, realistic galaxy clusters, and structures remarkably similar to those observed through telescopes. When dark matter is removed, the universe never develops the same complexity. Galaxies form too slowly, remain too small, or fail to appear altogether. This remarkable agreement between simulation and observation has become one of the strongest arguments supporting the existence of dark matter. Yet science is built on questioning even its strongest ideas. Researchers constantly challenge the dark matter hypothesis, searching for observations that might prove it wrong. This skepticism is essential because every great scientific theory must survive relentless testing. If new evidence contradicts existing models, scientists must be willing to revise or even abandon long-held beliefs. So far, however, every major observation has continued pointing toward the same conclusion. From galaxy rotation curves to gravitational lensing, from the bullet cluster to the cosmic microwave background, the evidence consistently suggests that an invisible form of matter dominates the universe. The cosmic microwave background provides another remarkable clue. This faint glow fills every direction in space and is often described as the afterglow of the Big Bang. It has traveled across the universe for nearly 13.8 billion years, carrying with it a snapshot of the cosmos when it was only about 380,000 years old. Tiny temperature variations within this ancient light reveal how matter was distributed shortly after the beginning of time. By analyzing these patterns with extraordinary precision, missions such as the Wilkinson Microwave Anisotropy Probe and the Planck satellite have measured the composition of the universe with remarkable accuracy. Their results independently confirm that ordinary matter accounts for only a small fraction of the total cosmic mass, while dark matter makes up a much larger share. It is extraordinary that light emitted billions of years ago still carries evidence for something that remains invisible today. As humanity continues exploring the cosmos, dark matter serves as a powerful reminder of how little we truly know. Every generation has believed it understood the universe, only to discover that reality was far more complex than imagined. The Earth was once thought to be the center of everything. Later, we learned it orbits the Sun. Then we discovered that our Sun is just one ordinary star among hundreds of billions in the Milky Way. After that came the realization that our galaxy is only one among trillions scattered across the observable universe. Now we face another humbling truth. Everything visible, the stars, planets, galaxies, and even ourselves, represents only a small fraction of existence. Most of the universe remains hidden, silently shaping the destiny of everything we can see. The search for dark matter is therefore much more than a hunt for an invisible particle. It is a journey toward understanding the true nature of reality. Somewhere in the darkness lies an answer that could reshape physics, deepen our understanding of the Big Bang, explain the formation of galaxies, and perhaps reveal entirely new laws governing the universe. Until that day arrives, the invisible matter surrounding us remains one of the greatest scientific mysteries ever encountered, quietly reminding us that the universe still holds secrets beyond our imagination. As the search continues, scientists are becoming more creative than ever before. New observatories are being built deep underground, where layers of rock shield delicate instruments from interference. Giant telescopes are scanning the skies with unprecedented precision, searching for the smallest distortions in the light of distant galaxies. Particle accelerators continue recreating conditions similar to those that existed fractions of a second after the Big Bang, hopping to produce particles that have never been seen before. Every experiment is another attempt to answer a question that has fascinated humanity for generations. What is the invisible substance that appears to hold the universe together? Some researchers believe the answer may arrive suddenly, through a single unexpected discovery. History has shown that science often advances in surprising ways. Radio waves, X-rays, pulsars, quasars, and even the accelerating expansion of the universe were all discovered when scientists were searching for something entirely different. It is entirely possible that dark matter will reveal itself in a way no one currently expects. A faint signal inside an underground detector, an unusual particle produced in a collider, or a strange observation from a future space telescope could instantly transform one of the greatest mysteries in modern physics into one of its greatest discoveries. Future missions promise to explore the universe with a level of detail that was unimaginable only a few decades ago. Projects such as the Vera C. Rubin Observatory, the Nancy Grace Roman Space Telescope, and the European Space Agency's Euclid mission are designed to map billions of galaxies and measure the effects of gravity across enormous distances. By studying how galaxies move and how light bends through space, these observatories will create the most detailed maps of the invisible universe ever assembled. Every new observation will either strengthen the current understanding of dark matter or reveal clues pointing toward an entirely different explanation. At the same time, advances in computing power are allowing scientists to simulate the universe with astonishing realism. Modern supercomputers can follow the evolution of billions of particles over billions of years, recreating the growth of galaxies, clusters, and the cosmic web from the earliest moments after the Big Bang. These simulations are becoming so accurate that they can predict subtle patterns later confirmed by real observations. It is one of the most powerful partnerships in modern science, where theory, computation, and observation work together to uncover the hidden architecture of the cosmos. Yet perhaps the most remarkable aspect of this mystery is how it changes our perspective on our place in the universe. Every object that has shaped human history, the earth beneath our feet, the oceans that cover our planet, the mountains that rise above the landscape, the moon that lights our nights, the sun that gives us life, and every visible star in the sky, belongs to a tiny minority of the universe's contents. The atoms that make up our bodies were forged inside ancient stars, but those atoms represent only a small fraction of all the matter that exists. Most of reality is made of something fundamentally different, something we have never directly observed. This realization is both humbling and inspiring. It reminds us that the universe is far larger, stranger, and more mysterious than our everyday experience suggests. We often think of science as a collection of answers, but in truth, its greatest strength lies in asking better questions. Every mystery solved reveals even deeper mysteries waiting beyond it. Dark matter is a perfect example. Decades ago, astronomers believed galaxies behaved in ways they fully understood. Instead, careful observation revealed an invisible universe hidden in plain sight, forcing humanity to rethink the very nature of existence. There is also a philosophical beauty in this search. Throughout history, people have looked into the night sky seeking meaning. Ancient civilizations connected the stars into constellations, sailors navigated by them, and early astronomers mapped their movements with remarkable precision. Today, our tools are more advanced than ever before, yet the sense of wonder remains unchanged. We still look upward with the same curiosity that has driven exploration for thousands of years. The difference is that now we know the stars themselves tell only part of the story. Behind every glowing galaxy lies an invisible foundation that silently shapes the universe. Perhaps one day a future scientist will stand before the world and announce that the mystery has finally been solved. We may discover that dark matter consists of entirely new particles unlike anything currently known. We may learn that gravity behaves differently under extreme conditions, requiring a revolutionary new theory of physics. Or we may uncover an explanation so unexpected that it changes our understanding of space, time, and reality itself. Whatever the answer turns out to be, it will almost certainly open new questions that we cannot yet imagine. Until that day arrives, dark matter remains one of the greatest unsolved mysteries in science. It cannot be seen, photographed, or touched, yet its presence is written across the universe in the motion of galaxies, the bending of light, the growth of cosmic structures, and the ancient glow left behind by the Big Bang. It is the invisible architect of the cosmos, quietly shaping the destiny of everything we know. The next time you look into the night sky, remember that the brilliant stars scattered across the darkness are only the visible surface of a much deeper reality. Beyond the light, beyond the galaxies, and beyond the limits of our current understanding lies an unseen universe waiting to be explored. Every new telescope, every new experiment, and every new discovery brings us one step closer to uncovering its secrets. Until then, dark matter remains a silent companion to every galaxy, every star, and every planet, a reminder that the greatest mysteries are often the ones we cannot see, and that the universe still holds countless wonders waiting to be discovered.